Okay, previously in lecture part 1, we have completely designed the basic dimensioning of the structure, whereby we have able to determine the plate girder web, the plate girder flange, and then the thickness of the flange. But we didn't carry out this check yet. Okay, so in this lecture or in this video, okay, we're going to learn how to check the allowable maximums, okay, for the plate girder, and then we're going to check the section classifications and whether or not the sections requires for the shear buckling check. So these are the 3 stars that we're going to learn in this topic. Okay, so basically let's go for the first one, which is check allowable ratio of the plate girder. Okay, the allowable ratio of the plate girder. So to check the maximum allowable ratio for the plate girder, okay, so now we check maximum allowable ratio of the plate girder. So HW over T has been explained earlier in the previous video lecture, which is from equations 5.117. Okay, you can have HWT equivalent to K E over FYF, and then we have AW over AF. All right, and in this case, we have calculated whereby K is equivalent to 0.4, and then we have 20, okay, 10 to the power of 3, 355, 1930 times 9 over 500 times 35, which finally resulted to 236. So this is the maximum allowable ratio. So when we designed our plate girder just now, okay, when we designed our plate girder just now, we have already determined that the BF, which is 500, thickness of flange 35, depth is 193, 35, and then the overall depth we decided to get about 2000 mm. So here in this particular case, therefore, this maximum allowable equation must be compared with the actual, okay, must be compared with the actual slenderness, ratio of the web. So in this particular case, you can see that our actual slenderness ratio, whereby here we have 1930, height of the web 1930, over the thickness of the web is taken as 9 mm. So then we get here 9. So then you will end up with 214. Okay, so in conclusions, okay, as a conclusion, with our proposed section sizes, in conclusion, the actual HW over T is lesser than the true HW over T. So this is the actual and this is the true value. So in this particular case, what we can conclude that this proposed sections, the proposed section is satisfactory. Okay. Okay, class. So just now we have completed the allowable check for the proposed plate girder, and we already found out that it is satisfactory. So now we move on to the next check, which is the classifications of sections. So for the classification of section, if you still remember, you can recall back earlier, table 5.2 C over TF, where we try to find this length C1 and C2 in video lecture 1, and we finally found out the total B, which is end up with 500. So in these examples, okay, when we define this, you recall that we have assumed that CTF must be lesser than 9 strain, where this allocate that it is class 1 sections. Okay, so because of that, our flange is classified as class 1. However, we didn't yet classify our web. So in this case, we then go again to the table, okay? We will see that C over TW, whereby our C is taken as 1930, okay? Eliminating the effect of the welded, okay? We ignore the welded length, okay? Ignore the thickness of the width, weld width. So then we get 1930 divided by 9, which is the thickness of the web. All right. So here you get 214. So 214 is larger than 124 strained. So when it is larger than 124 strain, you can see in the table, it is classified as class 4. So here, as I said earlier, in our chapter 1, usually different classifications of flange and web will be experienced or will be occur when you're designing plate girder. So in our case, our flange is class 1, whereby our web is classified under class 4. So, which classes is suitable for this particular sections? Earlier, okay, which has been explained in chapter 1. However, as explained earlier, a cross section is classified according to the highest least favorable class of its compression parts. So in this case, okay, if you look at web and flange, okay, for a plate girder, for a beam, all right, for a beam section or for a plate girder section, when you loaded the beam, okay, when you loaded the plate girder, so this plate girder will bend to certain actions. So it will then bend, all right, it will bend and it will bend. So when it bends, here it will experience a compression and here it will experience a tension. At the bottom fiber will experience tension. At the top fiber, it will experience compressions. Because of that, okay, because of it saying the highest least favorable class of its compression parts, in this case, web is not resisting any compressions. Okay, web is not favorable for the compressions. So therefore, to classify these sections, we will choose it become a class 1. Okay, we will choose it as a class 1 because for the compression part is a flange, so therefore we choose class 1. So in which cases we will choose according to web. Usually if you come across with the column, okay, usually you have a column. This is a column, all right, for the column. So for column, this is a column. So for a column, if you loaded it, so basically the web will be under compressions. So because of the web is under compressions, and if you are designing a column with a different strength, different yield strength, therefore what you need to do is that you need to classify based on the highest least favorable class of its compression parts. So in this case, you need to follow the web. But in our case, you have to we will follow class 1 because class 1 is the one, the flange is the one who going to resist the compressions. All right, so now let's proceed with the next design check. So we have done the section classifications and we can conclude that the plate girder sections in our proposed structure is class 1. So in this particular case, all right, the next step is we need to check whether the proposed sections are able to resist against the shear buckling or not. So here you need to refer to clause 5.12 EC3 part 15, whereby you can see there is two conditions. The first one whereby you can see for unstiffened web, the slenderness ratio of the web must be lesser than 72 over new strained, whereby if you look for stiffened web, they have another condition that you need to satisfy. So if you can see the notes highlighted there, if these limits are exceeded, resistance to shear buckling should be checked and transverse stiffness should be provided at the supports. So in these particular two cases, first you need to show whether our plate girder is unstiffened webs or stiffened webs. So for our case, we are actually designing for a stiffened webs. Okay, so then what we have to do next is we need to check whether HW over T is comply with the given equations here. Okay, now let's calculate the web design. All right, we need to check whether the requirement of shear buckling check. So as previously said, you need to refer to clause 5.1 to EC3 part 15. All right. So in this case, our structure is considered as the stiffened web. So for a stiffened web, okay, for a stiffened web, all right, so the equation is HW over T should be less than 31 new strained, and then we have the key factors. All right, so in this particular case, we need to know what is our end. Okay, let me continue with this. What is our end and what is our these factors, because here definitely we know it already. So let's find this parameter and check for a stiffened web. For this one, okay, we need to refer to clause 5.12 EC3 part 15 note 2 for steel grade S4600 and lower, so therefore the value of nu is equivalent to 1.2. For steel grades higher than S460, then it will given us value 1.0. So in our case, as our plate girder, the grade of steel is S355, therefore we have the value of end is 1.2. And how about this one? So for that particular value, okay, for that particular value, we need to refer whether A over HW is larger than or equivalent to 1, or another condition is that A over HW is lesser than 1.0. All right, so let's say we have these conditions or this condition, so we need to comply with the given equations for this value. So that parameter in this particular case is given as shown in clause 5.12 is 3.15, whereby in this condition it is given as 5.34 plus 4.00 HW over A squared. And for this one also, K equals to 4.00 plus 5.34 HW over A squared. So here, 4. A is the distance, okay, is the distance between the panels. So what does it mean by distance between the panels? So the distance between the panel means, if you look in our previous case, okay, this is our example. So we have the stiffness whereby located at 1.2, 2.55, 4.15, 6.25, and 10 meter. So A is representing the distance between the center of that stiffener with another center of the stiffener. So this is represents A value. So now we are doing the first one, okay? We are doing the calculating for each stiffness. So for the first one, A is 1.2. But for the second one is 2.55 minus 1.2, then we will get this A there. That is what it means by A value here. Alright, so once we have done that, we know what is A already. We know how to calculate K tau already, which is this, alright, the factor. So in this particular case, we have to check our HW over T. So we have calculate our HW over T, which is 1930 over 9. Either it is less than 31 over 1.2235 or not. So to do that, okay, in this particular case, we have to check this. To check this earlier, as I said, you need to know whether the A over HW is larger than 1 or A over HW is lesser than 1. So we then now calculate A over HW, which is our A, which is the distance. All right, so we are now doing the first one, okay, the distance from support, which is 1.2 meter. All right, so 1.2 over almost 1200 over 1930, we get 0.62, which is lesser than 1. So when it is lesser than 1, what does it mean then? It means that lesser than 1, we should choose these equations. Okay, so then these equations, all right, we have that equation now, whereby 4 plus 5.34 HW over A, and then you substitute the required equations, you get 17.8. So once you get that 17.8, finally you calculate and you found out that it is 214.4 is lesser than 80, is not less than, sorry, from 88.73, because it's not comply these conditions, which means the slenderness ratio is larger than the required given allowable. So as the limits are not complied, thus shear buckling should be checked. Therefore, we have to proceed with the next step, which is the shear buckling check, whereby we need to go for step 4, which is shear buckling resistance check, as this check is not compliant. Okay.